Thanks for joining us. So today we are concerned with locally convex vector spaces. So we are in the section about convex sets in locally convex vector spaces. So last time we had already a section about separating convex sets in topological vector spaces. And today we will try to separate in an even more stronger sense convex sets in locally convex vector spaces, which are special topological vector spaces. And so let us go right to the definition of a locally convex vector space. Or first, maybe let's have a reminder on the definition of a topological vector space. So first of all, remember that K was denotes in this chapter always a subfield of reals equipped with the order and the subspace topology induced by the reals. And when a topological vector space was a K vector space V together with a topology on V, if the vector addition and scalar multiplication are continuous and the singleton set consisting just of the origin is closed with respect to this topology. And so it turned actually out that when every singleton set is closed, because translations are homeomorphisms and that even more, it turned out that such a vector space is actually Hausdorff, right? So that was this proposition, right? So okay. Yeah, so that was a topological vector space. Remember also that here we have, of course, a product topology of the given topology on V with itself. And here we have a product topology of this usual topology on K, right, which is induced by the reals with a given topology on V. Okay, so now what is a locally convex? So now we come to a topic of today. So what is a locally convex vector space? So a locally convex vector space is a topological vector space, K vector space. So locally convex K vector space is a topological K vector space in which every point x, right? So if I have a point x here, for every point x in this vector space, each neighborhood of x, right? So say I have here a neighborhood of x contains a convex neighborhood of x, right? So I have here a convex neighborhood. Yes. So because in a topological space, translations are homeomorphisms in a topological K vector space, one can restrict here to requiring this for the origin. So, okay. So, good. So, an example conferred by the way 722, which consisted of examples for topological vector spaces. So in 722, we saw that K to the I equipped with a product topology for any index set I is a topological K vector space, for example, right? So this is actually even a locally convex K vector space. Why? Okay, so let's say I have a neighborhood of 0, for example, right? So 0, and then here U is a neighborhood of it in K to the I. And then now I have to find a convex set containing the origin and being contained in U. Without loss of generality, I can say that U is an open neighborhood, right? So, but if U is open, when it is a union of sets of a following form, product AI, I in I, where each AI is open in K, and only finitely many AI are different from K, right? So it's a union of such sets. And so the origin must be in one of these sets contributing to this union. So I find such a set, such a Cartesian product where the origin is contained. And then I said now BI is either AI if AI equals K, or I choose some epsilon I such that the interval from minus epsilon I to epsilon I in K is contained in AI, right? That's possible because the AI is open. So for each I in I choose such an epsilon, can choose it in K, positive one. Yeah, and then the product of the BIs, as you can easily see, is convex. And it is open in K to the I. So in this neighborhood U of the origin, I found a convex neighborhood containing of the origin being contained in it. Okay. So the next example is if a K-vector space V is endowed with initial topology with respect to a family of K-linear functions into the reals. Okay. So if it is endowed with a courses topology that makes a given set of K-linear functions continuous K-linear functions into the reals. So yes, when if we have additionally that for each point x different from 0, there is some one of these functions doesn't map this point to 0, when V is a locally convex K-vector space. Let's show this. So first of all, why is V then a topological K-vector space? That's the first thing to show, right? So V topological K-vector space. Okay, so here we have to show first that the vector addition is continuous. So we have to show that this map is continuous. So how do we, so if V is here endowed with an initial topology with respect to maps Fi, right? Etc. So how do you check whether such a map into such a topological space endowed with initial topology is continuous? Well, we have learned that you have just to look at all the compositions, and so this map is continuous if and only if all these composed maps are continuous, right? But to composed maps, let's look at one of them. So a composed map, Fi, for example, maps x, so Fy composed with the addition, right? Applied to some x, applied to x comma y. If x and y are in V, is of course Fi of x plus y, and that's Fi of x plus Fi of y. Yeah, and that's plus evaluated at Fi of x comma Fi of y. Right, and that's plus composed with the map x comma y goes maps to Fi of x, Fi of y. Yeah, where this last map goes from V cross V to R2. Okay, and this plus here is just the addition on the real numbers, so that's certainly continuous. You know that from your first semester at the university, at least. And so we have to show that this map is continuous. This map goes also into some space with equipped with an initial topology, namely the product topology on R squared, right? So, which is of course also the usual topology. So now we are looking at a map from V cross V to R that maps xy to Fi of x, Fi of y. I wrote the vectors here as column vectors, doesn't matter. R squared. So that's also equipped with an initial topology, and now the game begins again, right? So here I have a projection on the first and second component with respect to which is with respect to so in R2 I have an initial topology with respect to these two maps into the reals. So if I want to show that this is continuous, now I have to show it two compositions, right? First composition is, for example, xy maps to Fi of x, right? So and the second one is when analogous. So I'm looking now at a map from V cross V to R that maps xy to Fi of x. So I have to show that this is continuous. Yeah, but this is now a very easy exercise given the fact that Fi from V to R is continuous, right? I let you do this. Now, so that's why vector addition is continuous. Now let's look at scalar multiplication. So I think it's probably a similar game. Let's see. So I go here from K cross V. And I look at the map that maps a pair lambda comma x to lambda times x. And in order to show that this is continuous, again, I have to look at these composed maps. And so let's look at one of them. So the map from K cross V to the reals that maps lambda comma x to Fi of, where I is in I arbitrary, Fi of lambda x. But that's lambda of lambda Fi of x, right? So yes, and because the map, so this is now a scalar multiplication in the k-vector space R, right? So, and that's of course continuous also, right? So this map is of course continuous, right? So in the same way as before, I don't do every step now, but in very much the same way when before, it suffices to show that another map is continuous, namely the one where I go here to K cross R and map here x lambda comma x, the pair lambda comma x, to the pair lambda fi of x, right? And here that's the same game as here. So here I have again a product topology, so I can look at both projections. This time they give different things. So I have the first and the second projection are not analogous, but both are easy. So first I have here the map, and the projection is into here into K and here into R. So here I have a map that maps lambda x to, so the first composed map maps lambda x to lambda, right? And that's of course continuous. And the second one maps lambda x to fi of x. And yeah, and that's also, I mean, that's given that fi is continuous, that's again easy. Okay, so so vector addition and scalar multiplication are continuous. And now I show that the singleton set with the origin is a closed set. For that we will of course use this kind of separation property that you can distinguish. So one of the FIs for every point, for every non-zero point, one of the FIs can distinguish this point from the origin somehow, right? Okay, so so what do we have to show in order that the singleton set with 0 is closed? We have to take a point x different from 0, and we have to find a neighborhood of x that does not contain 0. So, but I can choose such an index I if I of x is not 0. So I find this I, right? And then I can choose an open subset of reals that contains a phi of x as an element, of course, but not 0, right? Yeah, that's clear that you can do this. And then yes, so when fi to the minus 1, fi to the minus 1 of a is, because fi is continuous, yeah, we have endowed it with a topology such that fi is continuous. This is open in V, an open subset of V, and X is of course an element of it, but the origin not. Otherwise, if phi of 0 would be in A, but if phi of 0 is 0 because Fi is linear, so when 0 would be in A. So the origin of V is not an element of the pre-image of A under Fi. Okay, so in this way we see that V is a topological vector space. Now we still have to prove this property that every neighborhood of the origin, if you want, contains a convex neighborhood of the origin. And that follows as follows. So remember the remember what we had here about initial topologies in general. So if we take the initial topology with respect to some maps, then it is generated by the pre-images of open sets, but you could also just say of pre-images of open sets from a generating system of a topology, right, on these NIs. Okay, so and in our case here, so I take the following generating system of a topology on R, namely the topology on R is of course, it's generated by these intervals here of a form, by open intervals in the reals, right? So it's generated by such intervals. So I know that each open set in my initial topology here is given by a union of finite intersections of such sets, right? Where I is arbitrary in I and AB are arbitrary in the reals. And therefore, if I have now a neighborhood of 0, let's call it U in V, right? So I have a neighborhood of 0, U in V, then it must contain a union of finite intersections of sets of this type, and therefore the origin must be in one of these sets contributing to the union, in one of these finite intersections contributing to the union. So I find actually a finite intersection here, over where the intersection runs over finitely many triples IAB, right? Consisting of an I in I and an A and B in R, such that this finite intersection is contained in U. Yeah, and this is, an intersection of convex sets is convex. So all these sets are open, of course, and an intersection of and they are also convex, right? Because if I is linear, each of these pre-images is convex, trivial to check, right? And an intersection of convex sets is of course convex. And yes, and so so you see that so that you have here and also a finite intersection of open sets is open. So we have here convex open set containing the origin. So that's a convex neighborhood of the origin in particular that is contained in U. So the next example of locally convex k-vector space is one which you know for a long time already. So you take normed real vector space, right? And so I mean, probably you never developed a theory of normed k-vector spaces where k is a subfield of the reals. So let's just think about the reals. every normed real vector space V is locally convex. Because, and when in particular every, I mean, of course, the topology comes here from the norm, right? So a set is open if for each of its elements you find a little ball around it with respect to this norm, right? Ball would be a set of all y in V such that the norm of y minus x is smaller than some positive radius, right? Yeah, so every normed real vector space is locally convex. First of all, it's a topological vector space, right? We have checked this when we defined topological vector spaces. So actually, it's because you know from analysis that vector addition and scalar multiplication are continuous. And the additional axiom that the singleton set with the origin is closed is also not a problem, right? So every norm, so it's a topological vector space, as we have already remarked, and it's and now now everything is easy, because if you have a neighborhood of 0, for example, then if you have an open neighborhood, so without loss of generality is open, and then it contains a ball around 0, right? So it contains a ball of some radius epsilon, and this ball, I've drawn a closed ball, but maybe that's okay. I could take a closed ball, but let's take an open ball. So that is convex, right? So why is it convex? So if it's a ball of radius epsilon, so you look at 2 points in it, so the norm of x and the norm of y, if these are smaller than a given positive epsilon, positive real epsilon, then you so why is this ball convex? So when you look at this convex combination, so you take an arbitrary lambda. Actually, I forgot here, for all epsilon bigger than 0, x, y, and lambda in 0, 1. So I have to complete this in the lecture notes. Okay. Yeah, so when this convex combination, this point on the line segment between x and y is again in the ball, of course. That's because of, properties of a norm. So you take a triangle inequality, and then you take a homogeneity, and then you get this is in fact strictly smaller. Okay, I need actually strictly smaller, because I was looking at an open ball. So let's say this is here. At some point it is yes, here you have strictly smaller, right? Maybe you need a case distinction for this, because if lambda equals 0 or lambda equals 1, when you have here the less than or equal, the strict less than or equal comes depending on whether lambda is 0 or 1, it comes from this or from this term. But anyway, it's true in the end. Okay, so have to correct this also in the lecture notes here. Okay. So normed real vector spaces and are locally convex, and yeah, so I think it's a good intuition to think of a locally convex k-vector space as something between normed vector spaces and arbitrary topological vector spaces. So we need now a little lemma for proving very good separation theorem for locally convex vector spaces. We need a little lemma. So suppose V is a topological k-vector space, and this lemma has nothing to do with locally convex spaces, and A is a closed set in it, and C is a compact set in it, when A plus C is closed. So let's prove this. Or maybe before we prove it, let's look at a counterexample if C is just closed instead of compact. Okay, so let's look in R2. So R2 as a topological R vector space. And let's look at the graph of the exponential function or something similar, right? And let's look at everything which is on the graph of the exponential function or above it, right? And that's of course a closed set. And now take another closed set, namely, so that's my A. Now take another closed set, namely just the first axis, right? So that's my B. Both are closed. And now A plus B, what is A plus B? Well, if we take here B and we drag it here, right? And you see that, okay, it's not very well drawn. But you see that you get actually A plus B will actually be the upper half plane, but without the first axis, right? So this will be A plus B. And that's not closed at all. But if a set B is now compact, right? So then you don't find so easily an example like this. Well, actually you don't find it like, as we will prove, there isn't. So suppose we have a set B like this, that is compact. And now if I drag it here at different places, you know, then, okay, like this, like this, like this. And so on. When you can easily imagine that you get always you know, that you get in the end a compact set again, right? So, but we have to prove this. We have to be careful with such statements, right? Let's prove it. So in this example, you would probably get when set like, you know, like this here. So let's prove it. So we have to show that A plus C is closed. That means the complement is open, right? So I take a point in the complement, and I have to show that there is a neighborhood of this point that is still contained in the complement. So every instead of saying there is a neighborhood of this point, I could also just say I have a neighborhood of the origin, and then I translate it to this point somehow, right? So because translations are homeomorphisms, every neighborhood of x is of a form x plus u, where u is a neighborhood of the origin. So I have to show that there is a neighborhood of x that does not intersect A plus C. That's what is expressed here. So now the proof goes as follows. So it's actually a bit different from how I illustrated the whole thing up to now. So up to now I always took this compact set and I dragged it around here, right? But of course you can just as well take this possibly non-compact set and drag it around here, right? So A plus C is actually the union over all these things here. And yeah, so we have here, we let here, so this is the origin, by the way, and we let here vary y inside C, right? And when we consider A plus y instead of we consider A plus y for this fixed y in C. Instead of A plus C, right? So we consider just A plus y, which is a subset of A plus C. And we try to solve this problem here for finding this U, this neighborhood U of the origin. Instead, we try to solve this problem only for A plus y instead of A plus C, right? So, and this we do for all y. So for all little y, we find a neighborhood uy of the origin, such that x plus uy intersected A plus y is empty, right? And now, so when the idea is that the intersection over all y's, where y arranges over C, that will then, as you can easily check, satisfy even that this intersection is empty, right? So there is a problem now because you always uys were neighborhoods of the origin, but if I intersect all of them, well, I don't have any guarantee why it should still be a neighborhood, because I intersect over possibly infinitely many. So the idea is now that you intersect only over finitely many. Okay, so let's wipe this out here. Okay, so the idea is that you choose, you look at D finite subset of C, and we will later have to think about how to choose it. And then you look at this thing here, right? So now the problem is that you know, uy was chosen such that maybe I should write this again here in blue. X plus uy. So for all y and z, uy is chosen such that x plus uy does not intersect a plus y. We will, yeah. So the problem is that you know, if I intersect here over all uys, then I have, of course, that this does not intersect a plus c. But now when I intersect only over some of uys, or finitely many in this case, then here I can just guarantee a priori that the intersection with a plus, and I write this in red, d is empty, right? And of course, instead of d, I would like to have here c, right? So the idea now is to choose uy a bit more carefully here, namely that you want uy here, actually you want to choose it in such a way that you have even here, instead of just y, you take the whole same neighborhood uy here, right? So that x plus uy intersected a plus uy is empty, right? And then I can here actually write this red thing here, I can then replace by the union overall y and d uy, right? And now I just have to choose this in such a way that c is contained in this red thing here, right? In this red union. So that's the idea. So when this is if d is finite, when this is a neighborhood, this is still a neighborhood of y, because d is finite. And yeah, so now the question is, how can I do this choice here, right? And there it helps me that I'm in a topological vector space, right? So we will see this now. So for each y and z, there exists a neighborhood uy of the origin such that x plus uy sorry, I forgot actually. I mean, uy was a neighborhood of the origin, so I have forgot to add y here. Sorry. So, yes, so, and here also uy plus y. Sorry for that. Yes, so x plus uy intersects y plus uy plus a, or does not intersect y plus uy plus a. And so I want to show this now. And for the same, I look at this map here from v cross v to v. X prime y prime, a pair x prime y prime of points in v is mapped to x minus y plus x prime minus y prime. So this is, of course, a continuous map, easy to check, because V is a topological vector space, and also the origin lies in the preimage of the open set. So I mean the origin of V cross V, that means that's 0, 0, where 0 is the origin in V, lies in the preimage of this open set. So, you know, A was closed, so the complement is open. And yeah, 0, 0 is mapped to x minus y, and yeah, x minus y is not in A. So otherwise x would be in A plus y, but this is contained in A plus c. And x is was not an element of A plus c, right? So hence there is a neighborhood uy such that, yeah, so actually there is, 0, 0 lies in this pre-image of this open set, so this pre-image is open again. So there is a whole neighborhood around 0, 0 where it still lies in the pre-image of a complement of A. Yeah, and by the definition of a product topology, there are neighborhoods of 0 in V and of 0 in V, right? Of 0 in V and of 0 in V, such that the Cartesian product of these two neighborhoods still lies in the pre-image of a complement of A, but I mean, I can intersect these two neighborhoods, right? And then, so I can take 2 times the same neighborhood. Okay, so and I can call this uy, okay? And so x minus y plus uy minus uy is contained in the pre-image of a complement. So the image of this is contained in the complement. So the image of uy cross uy is x minus y plus uy minus uy. It's contained in the complement of A. Yeah, so I could rewrite it like this, so that this set does not intersect A. And yeah, so that was the claim. Now, using this claim, so y plus uy, of course, is a neighborhood. It's a neighborhood of y, because uy is a neighborhood of the origin. Right, and these neighborhoods cover the whole of C trivially, right? And yeah, okay, the uy need not be open, but you could choose them open. If you choose them open, then the y plus uy, of course, form an open cover of C. And, you know, if uys are not open, you can make a similar argument. But anyway, there is a finite subcover. So there is a finite set D such that if y ranges over only D, there is a finite subset D of C such that if y ranges over only D instead of C, y plus uy still cover C, right? So by compactness of C, there is a finite subset D of C such that these y plus uy still cover C, even if y ranges just over D. Now, the intersection of this uys where y ranges over D, since D is finite, is a neighborhood of the origin. And we claim that this neighborhood does the job. So x plus u intersected A plus C is empty. And for this, it's enough to show that since the y plus uys cover the whole of C, it's enough to show that x plus u does not meet A plus y plus uy for each y in D. And for this purpose, it suffices to show that since u was the intersection over these uys when y ranges over D, it's enough to show that for each y in D, x plus uy does not intersect y plus uy plus A. But this holds even for all this holds even for all y in C, right? That was what we did in the claim. Good. So that proves this lemma. And now we can use this lemma to prove the separation theorem for locally convex vector spaces, which is our first main result in this section. And here I have copied theorem 7 to 10, which was a separation theorem for topological vector spaces, and its corollary 7 to 11, just to be able to compare it, right? So what do we have here? We again we want to separate two convex sets, right? So that's common to all these three theorems. So here A and C are again non-empty convex sets. That's exactly like here. A and B here were convex sets such that actually the interior of A is non-empty. In particular, A is non-empty and B is non-empty. And here we had the same thing, right? So in some sense, so you want, and you also want to do the same thing, right? So you want to separate, okay? So you remember that in topological vector spaces, here we could do this kind of rather weak separation here with a continuous k-linear function, right? Which was not a zero function, and in the special case that A is open, here we could do a little more. So we had kind of a stronger separation because we could squeeze in here a real number, such that phi of x is always strictly less than this real number here. Okay, so and the separation was again with a continuous k-linear function into the reals. Okay, but here we needed that A is open, right? And yes, so and here for topological vector spaces we needed that the interior of A is non-empty, and we had a rather weak separation. Okay, and now we have we separate again with a continuous k-linear function. Again with a continuous k-linear function phi from V to reals. But this time we have even much better, still much better situation, right? So we can squeeze in here two real numbers, okay? So we have here this thing here. Okay, that's still that looks still better, but we need that A is closed and C is compact. So that looks like a different thing here than what we had before. Suddenly A should be closed and not open, for example, right? But C has to be compact. Okay, so let's look into a proof. So we set B to be C minus A. This is closed by 734, what we have just proved, and 0 by hypothesis, because A and C should be disjoint here. The origin is not in B. So, and of course this is a convex set. And since V is locally convex, yes, look at the complement of B. The complement of B in V. So B is closed, right? B is closed in V. So the complement of B is open, right? So the complement of B is an open neighborhood of 0. It's an open neighborhood of the origin. But since V is locally convex, if you look at the definition of locally convex, then we have a convex neighborhood of the origin that is contained in the complement of B. A convex neighborhood of the origin that is contained in the complement of B, right? And yes, I can take this neighborhood open because the interior of a convex set is open. So I could just take the interior of this neighborhood. That's again a neighborhood, of course, and it is convex in view of 7 to 13, right? Because in a topological space, the interior of a convex set is convex. It's always convex. Okay. So we find, therefore, a convex open set, let's call it D, that contains the origin and doesn't intersect B because it's contained in a complement of B. Okay. And now I can actually use corollary 7 to 11, right? I can apply it on D, which takes the role of A, and B, which takes the role of B. Okay, so there is a continuous k-linear function, right? From V into a k-vector space, of real numbers, formed by the real numbers. And there is an R in R such that phi of x is smaller than R, less than or equal phi of y for all x in D and y in B. Okay. Now I call this R epsilon because it's probably a very small number. Why is it here a small number? Well, phi of 0, so phi is linear, so phi maps the origin to 0. And yes, so, and D contains the origin, right? So I have here in particular that phi of 0 is smaller than epsilon. So epsilon is positive. And if I take phi of x plus epsilon, for x in A and y in C, right? So if x is in A and y is in C, then y minus x lies in B, and therefore phi of y minus x is greater than or equal epsilon, and that amounts to say that phi of y is greater than or equal phi of x plus epsilon for all x in A and y in C. Yes, so I said epsilon could probably be very small. Well, I don't really know, but okay, the idea is that if A and C almost intersect somehow, which seems to be the hard case here, right? Then you could say that this x in some sense could get very close to a y here, and then the phi of x probably very close to a phi of y. So that's why I say the idea is probably that epsilon is small but positive. Okay. So because A is non-empty and C is non-empty, both are non-empty, I can form now a supremum over all phi of x where x ranges over A, right? Because phi of x are bounded from above, in fact, by every phi of y minus epsilon, if you choose y and z. Okay, and yeah, so this is a non-empty set bounded from above in the reals, so it possesses a supremum in the reals. And similarly, the set of all phi of y where y ranges over z is bounded from below, and it's also non-empty, so there exists an infimum in the reals. And yes, so moreover, we have that if you look at this inequality, you see easily that you see that actually phi of x plus epsilon is less than or equal this infimum for all x in A and y in C, for all x in A, sorry, and therefore the phi of x is less than or equal with infimum minus epsilon for all x in A, and therefore the supremum, that means R, is less than or equal S minus epsilon. So R plus epsilon is less than or equal S. Yeah, since epsilon was positive, we have R is strictly less than S. And R and S do when this job here. We will use the separation theorem just proved later for the Krein-Milman theorem, which will say that the compact convex subset of a locally convex k-vector space V is the closure of a convex hull of a set of its extreme points. So we should perhaps remind ourselves what was an extreme point. So we defined that actually already in 241. So if A is so that was actually defined here. K didn't need to be a subfield of reals, but it was actually an arbitrary ordered field. So, but anyway, so we defined that if A is a convex set, then a point x in A is called an extreme point of A if it is not the midpoint of a proper line segment in A, right? So and that's the definition, but we saw that it's also equivalent to not being not lying properly on a proper line segment within A, right? Yeah, so that was a little exercise to show that this is the same thing, right? So this definition here comes with less and actually what I said is true, and actually even more is true. You could even fix this ratio lambda, right? Strictly between 0 and 1. So if you fix lambda to 1/2, when this here says again that x is not the midpoint of a line segment, such a line segment, but if you fix it to 1/3, for example, when this says that it is not, it doesn't, your point doesn't lie on a proper line segment and divide it into 1/3 and 2/3, right? Okay, so yes, and so, and that was easy to prove, that instead of midpoints you could use these other ratios here. Yeah, that was a reminder on extreme points, but I will make examples in a minute again. But first, let me a bit generalize, in some sense, this notion of extreme point. Namely, we generalize it to a notion of a face. Okay, so what is a face? Let V be a k-vector space and A a convex subset. When a convex subset F, right? So I have a convex subset of my convex set, right? A convex subset F is called a face of A if whenever I have a line segment within A that, so the endpoints would be X and Y, such that the midpoint of this line segment lies in F, when both endpoints also have to lie in F, and therefore the whole line segment actually, right? So you see, if you take here a singleton subset of A, right? If you take for F a singleton subset of A singleton subset is always convex, of course, when the only element, if the only element of this singleton subset is this midpoint here, right? When when you see that in fact so let me call it Z, right? So if I have a singleton subset F equals Z, right? When this here becomes x plus y half equals Z, and this becomes also x equal y equals Z, right? So that means whenever I take the midpoint of a line segment in A, that means actually that Z is not the midpoint of a proper line segment within A, but because if it is the midpoint of such a line segment, then the line segment was trivial, right? So you see that this, if you apply this definition to singleton sets F, when a singleton set is a face if and only if its only element is an extreme point, right? Okay. So in this sense, it generalizes. But let us also draw some pictures, okay? So in order to understand it better, and for being able to draw in a better way, I just look at V R vector space R2. And I draw now in orange a convex set. So here I've drawn a convex set, right? It's convex whenever you take 2 points in it. The whole line segment between these 2 points lies in the set, right? So if I take these 2 points, then this line segment, right? So how is this to be interpreted? Well, here, this whole thing here should be in my set, right? It's actually the interior. And then this point should not be inverse set. This line segment should be inverse set. This point should be inverse set. This line segment should not be should be inverse set. Sorry, this point should not be in it. This dashed things are not inverse set, right? So, and this point is inverse set. No, I'm sorry. It actually cannot be right. It cannot be inverse set. I just see it now. So, because, you know, otherwise this whole, you know, the line segment between, for example, this point and this point would also have to be inverse set. So this point can't be inverse set. So let us correct this. Okay. This curved segment here is inverse set, this point is not, and this dashed curved segment is not inverse set, this point is inverse set. Okay, so I think it's clear how this set should look like up to some imprecisions in my drawing. Yes, so now yeah, let's look what are the faces of this set. What are the faces of this set? So first of all, if I have a point, let's first look if, so a face is always a convex subset, right? So, and if it contains a point, then and when you can look at all line segments on which this point properly lies, or you could say of which it is the midpoint, right? And let's first stick to the definition. So let's say it's the midpoint, right, of such a line segment. And when you know that this line segment also lies in the set, right? So here I know that with this black point, also this green thing lies in the set, right? Could make the green thing a little longer, of course, right? So black point should always be the midpoint, and so you see that that this has to be in the set, right? That roughly this has to be in the set, and so on. So that I don't know. So that this has to be in the set, right? And so you get a whole lot of points that must also be in the set, right? So I don't go into the details, but yeah, so you get certainly this whole region somehow, right? That must also be in the set. Yeah. Okay. So now, but then you could, you could play the game again, and you could take another black point here, and then you see that even this is in the set, and so on, right? And actually, if you think about it, well, we will make this precise in a minute. Then you will then you see that actually every face that contains this point here must in fact contain the whole set, right? Okay, so in order to make it precise, maybe let's first look at the later proposition here, namely that one, right? So it's again a characterization of faces, and like we did already for the extreme points some while ago, you see that you can characterize faces in another way normally in the definition we have here lambda equal 1/2, right? So we say that if the midpoint of a line segment lies in F, then the endpoints, and therefore the whole line segment lies in F. Okay, but here I could take another ratio, right? I could fix another ratio strictly between 0 and 1, and the same thing would be true. And so that's another characterization of faces. So it's again, as for the extreme points, we have this more general characterization of faces. And if you work with that one, when maybe you see more easily now, then let's play this game again. So we start with this black point, and now we see it more easily, right? So now I take this line segment here, right? And since this point lies properly on it, the endpoints lie also in my face, and therefore, so if I have a face of this convex set containing this point, then this whole line segment must be in it, including the endpoints, right? And so on. So for example, this line segment must be in it, right? So here I can't go right. So one of the endpoints must be really in the interior, because otherwise I get on this dashed thing here, which was not a part of my set, right? But I could go arbitrarily far, right? I could move it a little bit closer, and so I come actually arbitrarily far, right? And so if you look at this, when you easily see, right, that you can play this game in each direction, and when you see actually that everything here, really everything is actually an element of a face, right? But then if you take everything, that's certainly a face, right? If you take everything, then that's certainly a face. Because, you know, the condition is that it's a convex subset which satisfies this condition for a fixed lambda. In the definition we had lambda equal 1/2. Yeah, and if you take for F the whole set A, then that's trivially satisfied, right? Because F is a subset of A, and yeah, so you don't even have to look what's written here, because it's trivially satisfied that for all x, y in A, x and y are in A, right? Okay, good. So if what have you learned? If a face contains this point, then it's the whole convex set. If it contains this point, that's the same, right? So the whole set is a face, trivially of itself, and now maybe that's not the most interesting face. So let's look what other faces there are, right? Okay. So, well, what about, now we had already the whole set, what about the empty set? Is the empty set a face? Let's see, so the empty set is certainly a subset, convex subset actually. You may fix lambda to 1/2 if you like, and or you take another fixed lambda. And then the empty set is a face of A if and only if for all x, y in A. Whenever this thing is in the empty set, then, okay, we don't even have to read, right? Because this is never an element of the empty set, because the empty set is empty. And so here is a false statement. But if this is a false statement, then the implication is certainly true. Okay. Good. So the empty set is always, it's always a face. So there are always these two trivial faces, the whole set and the empty set. Okay. So now what other faces are there? So for example, if a face contains this point, if it contains this point, using this proposition, and actually we still have to prove this proposition later, but let's already use it. Using this proposition, you see again that, for example, since this line segment, so with black point lines properly on this line segment, and also on the same line segment a little longer here, and so on, and so on, and so on, you see that this whole thing here lies in my set, right? And now, is this actually a face, this green thing here? So maybe I should draw it more clearly. So the question is if this is a face, right? So let's look at it. So let's take some point on it, right? So maybe a red point. So if you take this red point here, you don't actually find, it's not the midpoint, for example, of any line segment within the green set. First of all, I should say that the green set is a convex subset of the orange set, so that's okay. Now, the other condition, so if you have a point in the face, the midpoint, for example, of a segment within of a line segment which is contained in A, then the whole line segment should be contained in the green set, right? But here I don't find such a line segment being contained in A anyway. So this red point is no problem. So let me then look at another red point, for example, this one. Now, if you have a line segment, a blue one here, contained in the orange set, then it's also contained in the green set, right? There's no other possibility here, right? So in this way, you actually see that this green set here is a face of the orange set, right? In the same way, you see that this green set is a face. Also, the singleton set consisting just of this point is a face. Easy to see, right? Because it doesn't lie on any proper line segment within A. It doesn't lie properly on a line segment within A, right? So if you take this, that does not lie in A, right? You don't find a line segment. It's not the midpoint, for example, of any line segment in A. So it is a face. So the singleton set, a set consisting just of this point is a face, or in other words, this point is an extreme point of this convex set. Okay. Yes, in the same way, you easily see that this point is an extreme point, right? Of this convex set. Or you see, for example, that this here is also a face, okay? And yes, what other faces are there? I guess we have all of them except this singleton sets here, right? For example, this one or this one, right? So there are a whole lot of extreme points. Probably up to some imprecisions in the drawing, every point on this curved segment here is actually an extreme point. Okay, so what faces are there again? So where is the empty set in this example, right? So where is A itself? Where is the empty set? There is what are the singleton faces? So what are the extreme points? Where is this one? Where is this one? And here all these points are extreme points, right? Well, and when where is this face, right? Where is this? And where is this? And I guess that should be all. Okay, so that's for understanding faces. Okay, so now let's go back again. So we had this definition of face, and we first have to prove something. So we had this definition of face where we set for lambda to be 1/2. So suppose now that V is a K-vector space, A is a convex subset, and X is an element of A, right? When X is an extreme point of A, if and only if a singleton set with X is a face of A, right? That follows directly from a definition 241. Okay, let's look at it again. If A is a convex set and X is an element, it's called an extreme point if there are no Y set in A such that Y is different from Z and X is the midpoint, right, of Y and Z. So it's just a different formulation, easily seen to be equivalent. Okay. So but I have here a formal proof. So X is an extreme point of A. Formal proof of this proposition. X is an extreme point of A. By definition, if and only if there doesn't exist Y set in A such that Y is different from Z and X is the midpoint of a line segment between Y and Z. And so that I can reformulate this by saying for all Y and Z, this is not true, right? So this is not true. You could say that this conjunction is not true means whenever the second part of it is true, when the first cannot be true, right? When this inequality here cannot be true, so there must be equality. Okay. But then you see that if Y equals Z here, then this is actually Y plus Y half, but also Z plus Z half. So when X must actually equal Y and Z. Okay, so I could also write it in this way. Just a slight reformulation, and then you could write that Y plus Z half lies in the singleton set X, and then you could rewrite that Y and Z lie in the singleton set. And so now I've written it in a way so it becomes obvious that this is equivalent to the singleton set with X being a face. So that was easy. So now we have to still to prove this proposition, which we did not yet prove. Although I guess we had a similar statement for extreme points. So in 242, we had already something similar, right? So here we said, so it was very similar. It was more or less the same thing. as an exercise. But that was only for extreme points. Now we have it for faces. So let's prove it. So from B to A, well, from B to A, that's really an easy exercise. What's the idea here? So here I'm saying whenever whenever I have a line segment and the point on this line segment that corresponds to a certain ratio, strictly between 0 and 1, if this point lies in the face, then x and y lie in the face, right? And then I have to show that the same thing is true with the ratio 1/2. Well, that's really easy. So if I have here, so if I have here a set that satisfies, if F is a convex subset satisfying B, right? So, I don't even draw it, and now I have a point in F, let's say this one, which is the midpoint of a line segment in F, let's say of this one, right? Then you can now look. Now I have to show that the two endpoints here are also in F, right? And for this aim, I can look at two shorter line segments, right? So I can first look at this red one. Now it depends what lambda is, right? So if lambda is maybe 1/3, then it will perhaps look like this. So I want that the black point divides this red line segment with a ratio 1/3, 2/3, right? Okay, and I look at another one, the green one, where I shorten the other part of a blue line segment, right? And by applying condition B to both the red and the green thing, right, I get that the endpoints of the red line segment, but also of a green line segment lie in the face, right? And I'm actually interested only in this endpoint of a red line segment and this endpoint of a green one. And they lie in F, and they happen to be, or they are by construction, exactly the endpoints of a blue line segment, which lie then in F. Okay, so that was really easy, but maybe you should write it as an exercise. Now from A to B, that's an argument that is a bit similar to what we did already for, or that is actually really similar to what we did already here in this exercise, right? Where we did the same thing just for extreme points. We fixed this ratio lambda, and whereas in the definition we take the ratio 1/2, we can take here another fixed ratio strictly between 0 and 1. Okay, so let's do this. So assume that F is a face of A. So F is a face of A, but B is not true. So there is a counterexample to B. So but there are X and Y in A, such that this is not true. This implication is not true. That means this here is the premise of implication is true, but the conclusion of implication is not. Right? So So the conclusion is not true. So either, well, not either, but it's not an exclusive theorem maybe, but x is not in F or y is not in F, right? And yeah, by interchanging the role of x and y, you can do this if you replace the ratio perhaps by lambda by 1 minus lambda. You can just say x is not in F, right? So without loss of generality, x not in F. Okay. If lambda is so maybe let's make again a little picture. So we are heading for a contradiction, and I don't even draw the face F. So maybe the face F is this thing, right? But I don't even draw it. So now F is this face, and I have so lambda, for example, could be 1/3, right? So I have it. So I have 2 points x and y in A. Let's say this is x and this is y. And so if lambda is 1/3, then this is x third plus 2/3 y. So it's closer to y than to F. So it would be this point, right? Right. If lambda is 1/3, for example, right? So if lambda is 1/3, as an example, when this would be lambda x plus 1 minus lambda y, right? And yeah, and x should not be in F, right? And I'm heading for a contradiction. So if x is not in F, right? But this thing is in F here. Okay, so yeah, if now since lambda was 1/3, this is this point is closer to y than to x, right? So it divides this line segment here with this ratio 1/3 here and 2/3 here. And here I will have to do something, right? So it would be bad. I mean, it would be easier if this black point were closer to x than to y, right? That means lambda would be bigger than 1/2, or this or bigger than or equal would even be okay. So if a black point would be at least as close to x than to y, right? If it were, for example, here, then it would be much easier, right? What would I do when I just take the line segment whose one endpoint is x and the other one is somewhere on the line segment between x and y, such that the black point is the midpoint of its green line segment. And since it is the midpoint, and since the black point is in F, both endpoints would have to be in F, and then I have already a contradiction because x was not in F, right? So that's the easy case, but we suppose we are in the harder case where the black point lies closer to y than to x. Okay, so lambda is smaller than 1/2. Okay, so and in this case, the idea is now to change x, right? To change x, to change with blue segment, to make it actually shorter, so that when ux would be actually here, the midpoint between the old x and the y, right? So that would be my new x, my x prime, let's say. So, but why is when the black point is again on the line segment between my new x, my x prime, and y, but with a different lambda, which is now, well, I don't know if it's in my picture, it's already now bigger than 1/2. But in general, it could still be much smaller than 1/2, right? If the original point was very, very close to y, when lambda will be still small, but it will be much bigger already, right? Okay, so but yeah, but it's clear that you quite quickly, if you iterate this many times, when you will very quickly, in fact, come into a case where lambda is bigger than 1/2, right? Why can you actually do this even once? So because we of course want that the new x, that means the x prime, is again not in f, right? When we can forget about the old x. Why is the x prime again not in f? Well, if it were in f, since it is the midpoint between the old x and the y, when both x and y, due to condition A, would have to be in my face, but x was not, right? So that's the whole idea, right? So if lambda is smaller than 1/2, I replace x lambda by x prime comma lambda prime, where x prime is a midpoint between x and y. And yeah, if just a note that for lambda prime, we can take 2 lambda, which is smaller than 1, right? Because lambda was smaller than 1/2. And it's also bigger than 0 because lambda was bigger than 0. Yes, so lambda was bigger than 0, right? Because when we have that x prime is not in f, since A is convex and f is a face of A, right? And yeah, and x is not in f, right? Lambda prime is again in the interval 0, 1, k. And we have that lambda prime, x prime, plus, that's in some sense here I verify that lambda prime is really the new ratio, right? That's the new ratio. So lambda prime x prime plus 1 minus lambda prime y is, let's just calculate this, 2 lambda times x plus y half, right? Plus 1 minus 2 lambda times y. Now let's just calculate. So what is the factor that x is, what is the scalar x is multiplied? So here I have 2 lambda is multiplied with, so here I have 2 lambda divided by 2, that gives lambda, and here I have nothing that contributes to x, so I have lambda x, and here I have 2 lambda, I have lambda contributing to y, and minus 2, yeah, I have lambda contributing to y, and then 1 minus 2 lambda contributing to y, so in total I have 1 minus lambda times y. Yeah, so I see this is really where lambda prime is actually the new ratio, right? Okay, so by iterating this in case of need finitely many times, and actually it will go very quickly in practice, one at least if if yeah, at least if my black point here is not very, very close, is not extremely close, if my black point here is not extremely close to y, somehow I deleted y, I think, don't know why. Okay, so so it's over there. Sorry, something has I see. So okay, so yeah, we get quickly into a case where lambda is greater than or equal 1/2, right? Okay, so formally again, because we double lambda each time in each step, and of course, if we start with a positive lambda, we will very quickly we'll get, after finitely many steps at least, we get into a case where lambda is greater than or equal 1/2. And then now I do the easy case I have already mentioned, right? So in the easy case, I shorten this line segment so that x divides it with ratio 1/2. So that means I keep the point x, and the other endpoint of a new line segment will be z. Okay, so maybe let me update the drawing a little bit. So now we are in a case where, yeah, now we are in the case lambda greater than or equal 1/2. So I have here my x, I have here my y, and the black point, that's the black point should be, in fact, this point here, which lies in f, is here. It's closer to x than to y. So it's lambda x plus 1 minus lambda y. Right, x was, by the way, not in f. And now I look here at this line segment such that the black point is the midpoint of it, and one endpoint is x and the other one is z, right? So that's the idea. And yeah, so if you see here, we will actually define z in such a way that x plus z half equals exactly the black point, right? And so let's, so I did this, I mean, you can come up with it yourself, but I did it for you. So we have here, I define z in this way, so I start here. So maybe the idea is even present here. So I start here with x, right? And then when I add 2 times, so what do I have to take? So I take the black point minus the blue point, right? Maybe let's even, so a black point minus the blue x, right? So that's the vector from here to here, right? And you add it 2 times, right? Because you have to go again so that it gets a midpoint, right? So yeah, so let's just calculate that everything is okay. So I have here x, so what contributes to x with? So I have here 1 plus 2 lambda minus 2. So I have 2 lambda minus 1 that contributes to x here. So the scalar before x is 2 lambda minus 1. And for y I have 2 times 1 minus lambda here, right? And when I don't have anything else, right? And this is you know, because lambda is greater than or equal 1/2, this is actually, yeah, so this is greater than or equal 0, and it's certainly less than or equal 1, right, because lambda is less than or equal 1. And 1 minus, maybe let me point this out, that if I take 1 minus this yellow thing, 1 minus it, this is 2 minus 2 lambda, right? So it's 2 times 1 minus lambda. Okay, and that's actually what is written. What is so sorry, I have some problems here. Okay, so that's actually what is written here, right? So that's actually a convex combination. Okay, I even did this calculation here. Didn't see it. So these two things are, yeah, greater than or equal 0, and they add up to 1. So that's a convex combination. And x plus z/2 is x, yes, x plus z/2 is, so if you add here an x, right, to z, then you get here 2 lambda instead of 2 lambda minus 1. And if I divide them by 2, I get I get lambda x, and here plus this orange thing divided by 2 is 1 minus lambda y. Yeah, here I did the calculation in another way. Sorry, here, yes. So, yeah, here I divided by 2. Yeah, you can also do it in this way, that you say that's x/2 plus x/2 plus this divided by 2. So that's how I did it here. And when you see it again, so that's lambda x plus 1 minus lambda y. Yeah, because x minus x is 0. And that's the old, that's the black point, so that lies in F. And therefore, because of my condition A, that F is a face of A, which is exactly this condition when with lambda equal 1/2, I get that since x plus z/2 lies in F, I know that x and z lie in F. In particular, x lies in F, which is a contradiction to x not lying in F here. Okay, so contradiction. So a proposition is proven. Okay. Now we come to some examples. So first example, I think I said already that if you have a convex subset of a k-vector space, then always the empty set and this respective set, they are both faces of A. And we call these the trivial faces of A. So the second thing is that second example is just a square in R2. So I think I already showed you how you get to know the faces. And here we have again, of course, the empty face, the whole set as a face. Well, when you have here the 4 corners, with one, with one, with one, and with one. That gives 4 singleton faces. That means 4 extreme points. These are the extreme points, or at least these are extreme points. All right, so in fact you see that they are exactly the extreme points, quite easy to see. So these 4. Then you have this guy here. Okay, so it will be this one, right? And also this one, right? And so that's of course this one. And then, yeah, of course you have also these 2, right? So that's the sides of a square. Yeah, so now I just color them with the same color. Right? And then finally you have, yeah, and that's it. I can easily see that is everything. Okay, so next example is a closed disk like this in R2. So here, well, what are the faces? So of course, again, the empty set and the whole convex set. But when we have here, otherwise we have, you know, if something from the interior is in it, then you see easily that everything is in it. So, if you have something on the boundary which is in your face, then either, you know, if you have something on the boundary which is in your face, then either, then the question is, can it happen that some other point of a boundary is also in this face? Well, if this were the case, since the face has to be convex, the whole line segment between these 2 points would have to be there. But that means an interior point would be an element of a face, but then the face would again be everything, right? Okay, so in fact, for all other faces, it's true that they consist just of 1 point on the boundary. And actually, if you take 1 point on the boundary, you see easily that it is a face because it forms a convex subset. And you don't find a little line segment within the disk where this point is such that this point properly is on the line segment, right? You cannot find this, right? So yes, so it's an extreme point. And yes, so all points, so extreme points are exactly here the points on the boundary, and if you see them as singletons, then they are the faces, the non-empty, non-trivial, well, the non-trivial faces, right? The non-trivial faces are exactly these singletons consisting of extreme points, and the extreme points are in this case the points of a boundary. That must not always be like this. Okay, good. If you take now the open disk instead, then you see, with almost the same arguments, that you see that there is only the trivial faces, right? And so a whole set and the empty set. now we come to a definition of an exposed face. So it will turn out, but it is not part of a definition, it will turn out that an exposed face is actually a face. So that it seems appropriate to use this terminology, right? But for the moment, this is not part of a definition. So these are special kind of faces. And so let V be a k-vector space and A be a convex subset. We call F an exposed face of A. If there is a k-linear function from phi from V to a k-vector space of reals, such that F consists of those points of A where phi gets a maximal, right? So F is a set of all x in A, where phi is maximal among all points of A, or minimal actually. I mean, doesn't matter, I could exchange phi by minus phi. Here I chose, here I decided that in the definition I require that these are the points where phi is minimal, right, among all points of A. Good. So for all y in A, phi of x less than or equal phi of y, right? So of course there does not always have to be such a point where a given k-linear function phi from V to the reals gets minimal. So yes, so for example, take k equal r, v r2. That's the case I can draw really, and let's take for phi, well, any non-trivial linear function. So for example, xy maps to x, just a projection on the first coordinate. And now you know phi, where is phi actually 0? Well, phi is 0 here, right? Where is it 1? Well, it's 1 here. Where is it minus 1? Right, so here phi is 1. Let's say phi is 1. I write it in a little bit sloppy way here. Here phi is 0 and here phi is minus 1. Right? Okay, so but since in this picture the boundary should not belong to a set, you see that the empty face is actually that this set here, for this given phi, right, and for this given A, this set is actually empty, right? So so we only, and this happens also for other non-trivial phis, right? So for example, the projection on the y coordinate, on the second coordinate, the picture would just look differently. Like these things would be horizontal lines then, right? Or if you have any other non-linear, non-trivial, non-zero phi, right, then you would have a similar picture with some other lines here. Yeah, so you see that you always get here the empty set only. And if the only exception is where phi is the zero function, right? Zero function is always a k-linear function, but constant zero function. In this case, you get here the whole set A, right? So that argument actually shows that the whole set is always an exposed face of itself. Yes, and I guess yeah. So in this example, the whole set and the empty set are the only exposed faces, right? So the empty set, by the way, need not always be an exposed face. Indeed, if you take the very same example, but you take now a closed disk, instead of the open one, then you see that you get you don't get the empty set here, no matter what phi is, right? So here the empty set would not be exposed. So the empty set need not always be an exposed face, although it is always a face, right? And so the idea is, let's maybe look again at this example, the closed disk, the closed unit disk. Here you see easily that if you look at this phi here again, then you see easily that you get that this singleton set consisting of just that extreme point is actually an exposed face, right? We know already that it's a face, but it's also exposed, right? By taking other phis, right? For example, if you take projection to a y coordinate, when you get that this point, the corresponding singleton set is an exposed face, right? But you can do this with every point, so this point is also exposed. But before we look at more examples, let's perhaps first prove that an exposed face is actually always a face. So that's the proposition part of this 7310 is that every exposed face of A is a face of A. We have to prove this. So let's prove it. Let F be an exposed face of A. We want to show that F is a face of A. Well, it's easy to show that F is convex because it is of that form for some k-linear function phi from V to the reals. Yeah, so just check it, right? So if you take here an x1, let's say, satisfying this, and when you take an x2, so you have an x1 satisfying this, when you have an x2 satisfying the same thing, right? Now you take a lambda between 0 and 1, actually in k, right? When you have phi of lambda x1 plus 1 minus lambda x2. We have to check that this is less than or equal phi of y, but that's, lambda phi of x1 plus 1 minus lambda phi of x2 is less than or equal lambda times phi of y plus 1 minus lambda times phi of y, right? Because of these two inequalities here, and when we are done, right? When this is equal to phi of y. And that's true for every y in A. Okay, so so it's really easy to check that F is convex. Need to check this if you want to show that F is a face of A, because that's part of a definition of a face. So it remains to show that if we have a line segment within A, or within A, such that the point of F is the midpoint of it, when the endpoints of this little line segment also lie in F. Okay, so for this we choose a phi that witnesses that our face is exposed. So we choose a k-linear phi such that exactly this is true. And now we let x and y be in A such that the midpoint of a line segment between x and y lies in F. We have to show that the endpoints x and y of this same line segment lie in F. That means the whole line segment lies in F because F is convex. And it is obviously enough to show that that phi of x equals phi of x plus y half equals phi of y, because this is that x plus y half is one of the points of A where phi gets minimal, and if x and y if phi takes the same value on x and y as it does on x plus y half, well, then x and y are also points where phi gets minimal. Where phi takes a minimal value among all points in A. Yes, so we have to show this. We know that phi of x plus phi of y equals that's 2 times phi of that's 2 times phi of x half. Maybe let me write it like this. So that's that's just because of the linearity of phi. So in fact, the right hand side is phi of x plus y, and that's because of linearity, because of additivity of phi is phi of x plus phi of y. That's just because phi is linear. Now this is because x plus y half lies in this set. This is, and x and y lie in A, so I can actually write that. So this is less than or equal phi of x, and this is less than or equal phi of y, and so I have phi of x plus phi of y is equal this, is less than or equal this. So in fact this is not, this is first doesn't seem to help anything, because here I have already that it's actually equal, so that's actually an equal. But the point is that actually that would be a strict inequality here if phi of x plus y half would not be equal, if it were not equal to both phi of x and phi of y. Okay, so maybe in the lecture notes I should actually make this more clear. So the point is really that this is actually less than or equal phi of x, and that is less than or equal phi of y. And the reason for these is, are these two things. Every time this is the reason in both cases, right? And then if phi of x or phi of y would be different, were different from phi of x plus y half, then I would have here a strict inequality. Let's see if I can make it more clear in lecture notes. Okay, so yes, okay, so and strict inequality would of course be absurd here, because phi of x plus phi of y cannot be strictly smaller than phi of x plus phi of y. Hence, phi of x must be equal to phi of x plus y half equal to phi of y. So that was what we wanted to show. So every exposed face of A is a face of A, legitimating now this that we call it an exposed face. Okay, so Now let's look at some examples, and I take again the same examples as before. Right, so and one additional example then. So the first example is, of course, I guess I said already that for a convex subset of a k-vector space, it is always an exposed face of itself. That's because I can look at this constant zero function phi. And I already said also that the empty set might be exposed or not exposed. So I already said that for the closed unit disk in the R vector space R2, it is non-exposed, and for the open unit disk in the R vector space R2, it is exposed. So I already said this. Now all faces of a square are exposed except the empty face. Well, the empty face, why is the empty face not exposed? The argument is similar to what we have seen for the closed disk. You could argue like this. You could say this closed square here is compact because it's bounded and closed, and it's a non-empty compact set. And on this non-empty compact set, every continuous function assumes a minimum, right? And that show, and in particular every linear function, every linear form takes a minimum, and yes, and so every face contains every exposed face contains an element. So the empty set is non-exposed. So all other faces. So what other faces did we have? So the whole set. What about the whole set? Well, that's defined by the constant linear form, right? So, and so what about this exposed face? Well, here I could, for example, take the phi from R2 to R. Let's see what will work. So projection on the first coordinate will not work, because that would actually give this face here. Or actually, sorry, it would actually give this face, because I'm looking at the points where phi gets minimal. Yes, so that would not work. Projection on the y coordinate would also not work, because that would give this thing here, right? So so but what works is actually phi goes to, I mean, there are many linear forms that work, but one of them would be this one, right? So if you take xy goes to minus x plus y, when you get, in fact, it takes its minimum exactly on this point, right? Yes. I guess now you see that all faces, you can do that for all faces, right? because we have already seen for the sides of a square, we have seen already how to do that. And now I've shown you how to do it for the corners here, and for the whole convex set, for the whole square, you take phi over 0 function. Okay, so yeah, what about the closed unit ball? So for the closed unit ball, we had the trivial faces, the empty set and the convex set itself, and we had the only other faces were the singleton sets consisting of one point on the boundary, one point of unit circle. Okay, and yeah, let's maybe start with these singleton sets. They are exposed, right? Because, you know, it's easy to find a linear function that into the reals that takes on here, let's say phi, right? That takes on the value -1 here, right? And yes, or actually some other non-zero value would also do it. Some other negative non-zero value, some other negative value. Yes, so okay. Yeah, so that these faces are exposed, and when we have, what about the trivial faces? The whole set is always exposed, taking the constant 0 function for y, and the empty set is not exposed here, the same argument as for the closed square, because every linear form, every R linear map from R squared to R, so every linear form on R squared takes a minimum on this non-empty compact set. Okay, so all faces of a unit disk are exposed except the empty face, which is not exposed. So now if I take the open unit disk, this had only the trivial faces, the empty set and the set itself. The set itself is again exposed. What about the empty set? Is the empty set here exposed? Yes, it is actually. Take any non-trivial, non-zero, R linear map from R2 to R, right? And for example, doesn't matter, but like for example, the projection on the first coordinate, and when you see, so what are the points where this is minimized? So what are the points where the projection on the first coordinate is minimized? Well, there is none, right? I mean, it gets smaller here and smaller, but you couldn't always find another point for which it is still smaller. Okay, so the empty face is also exposed, so all faces are exposed in this case. Finally, we give an example which has exactly one non-exposed face. So, namely, I take, so in R2, consider the parabola, y equals x squared. So, y greater than or equal x squared would then be all these things here, right? Together with the parabola itself. But I do that only for non-negative x, and if you want y. So I take, in fact, only this here. And when I take the union with this, right, which is this quadrant here, right? So in the end, I take, you know, in the end, I take exactly a set. It looks like this. Right? And so now what are we faces? Well, the empty set, in fact, is a face, because you could take, well, the empty set is always a face, sorry. We will see that it is also exposed, right? The empty set is always a face. The set itself is always a face. Now think of what are the other faces, if you think about it. If a point in the interior is in a face, then the face must be everything. If a point in the boundary, when there are different types of points on the boundary, if a point on the boundary is in the face, if this one is in the face, then you in fact get immediately this line segment, right? Which is unbounded, unbounded line segment. If so, this is a face. Then another face would be consist just of this point, right? Yes, because it does not lie on a proper line segment. It does not properly lie on a line segment contained in the orange set, right? Such a line segment, well, you see it's not possible, right? So so this is actually an extreme, it's an extreme point. Then well, also all other points here, right? So this one, all other points on the boundary are extreme points. And if now yeah, if and actually that's all easy to check, right? So these are the faces, and now which of them are exposed. So let's start with the empty face. The empty face is exposed because you could take, for example, for phi, the map projection on the first component, for example, right? Because there is, for every point in the orange set, right, there is still another point, right, which is to the left of it. So that means the value of phi is still smaller. So you never get, so you have no minimizer on the orange set for y. And yeah, and that means the empty set is a face, and the whole set is always is an exposed face. The whole set is always an exposed face, because I can take the zero function here, as you know already. So that does the job for the whole set. When we have this line segment here, for this line segment, I guess it's clear what you do. You just take a projection on the second component, showing that this is an exposed face. Now for such a point here, it's easy to see that you find the corresponding phi, right? That cuts out in some sense this point, right? And that let's say this line consists of points where phi gets maximal, right? It's always easy to find. Now where is for this point is the only point that could potentially be different, and in fact it is, right? Because yeah, if you take a phi whose the kernel of such a linear form phi here, if phi is not the zero map, is a straight line through the origin, right? And now look at if and on, so for example with straight line through the origin, and on one hand, on one side of this straight line phi will be positive and on the other negative, or vice versa. And so but you see if a line has so what about, maybe let's first look at the two x's, right? So if the kernel of phi, which I draw here in green, is the x-axis, then depending where phi is positive and where it is negative, on which side of this green line it is positive, and on which side it is negative, you either get that phi is minimized on the empty set, or it's minimized on this face here, right? So let's look at the other axis. For the other axis, you either get again the empty set, or you get actually always the empty set. Yes, you get always the empty set. And now let's look at the phi with, so let's look at the case where this kernel is a straight line with positive slope. In this case, you get, either the empty set, or you get, for example, this point, you get actually 1 point on this segment here, right? So one, in our case, it would be that one, right? If it is a straight line with negative slope, like this one, then you get again the empty set, right? So you never get actually this point. You cannot get it, right? So you cannot cut it out somehow, right? Right, it's not possible. Let's look at it again. So that doesn't do what, it's not very well drawn. That doesn't do a job, right? That doesn't do a job, and so on. But then, if you don't have positive slope, that also does not do a job, and so on, right? So, it has exactly one non-exposed face, namely this, consisting of this extreme point, namely the origin, right? So, okay, the next proposition. So, suppose V is a k-vector space. A is a convex subset of V, and F is a face of A. Now, being a face of A, F is in particular, again, a convex set, okay? So I can ask about what are the faces of this convex set. So, what are the faces of a given face, right? That makes perfect sense to ask. Now, okay, faces are always subsets. So let's take an arbitrary subset of F. And let's ask if it is a face. And here I claim that G is a face of F, if and only if it is a face of A. Okay, so showing that the faces of F are, if you know exactly what are the faces of A, then you know also what are the faces of the faces. Okay, of A. Good. So let's prove it. So if G is a face of F, now we have to show it's a face of A. Well, certainly if it's a subset of F, then it's a subset of A, and it is also convex. So now let X and Y in A such that X plus Y half lies in G. We have to show that X and Y lie in G. Now, if X and Y are in F, then this is by the definition of a face of F, right? So, but the problem is that X and Y are here in A, a priori at least, right? Yes, so we have to show that X and Y are in G. Because X plus Y half lies in G, which is contained in F, we have that X and Y lie in F. Yeah, and then we are done. Yeah, here I use, of course, that G is a face of F. Okay, so now, yeah, if X and Y are in F, we are done. Since G is a face of F, it follows that X and Y are in G. Okay, for the other direction, let G be a face of A. And let X and Y be, now we have to show that G is a face of F. For this we have to show first that G is a subset of F, but that was the global hypothesis here. So so here we need this, now since G is, of course, if it's a face of A, it's convex, so that's okay. So the only thing we have to check that if X and Y are in F with X plus Y half lies in G, that when X and Y are also in G. Yeah, but this is really easy. So because X and Y are in A, because F is a subset of A, then we have that X and Y lie in G, because G is a face of A. So that was very easy. So remark, every intersection of faces of a convex set in a K-vector space V is obviously again a face of this convex set. Here I just realized that one has to be careful with this statement, because you could think that I can take the intersection over the empty system of sets, right? You could also write it like this. The empty system of faces, right? That is, that you could say is the empty intersection, but it is not empty at all. It would by definition certainly be V, right? And of course V is not always a face of a given convex set, only if a given convex set is V itself. Because a face has to be a subset, right? So so how to say this? So if I write here every empty intersection, every non-empty intersection, then this could be misinterpreted, because you could think that you don't intersect over the empty set here, right? But you actually ask for the intersection to be a non-empty set, right? So okay, so I don't know how to what's the best way of expressing this concern. For the moment, let me just write except possibly the empty intersection, which is V, right? Every intersection of faces of a convex set in a k-vector space V is obviously again a face of this convex set, right? Because if you are not in this exceptional case, then I have to correct this in the lecture notes. If you are not in that exceptional case, then this intersection will again be a subset. It will again be convex because an arbitrary intersection of convex subsets is obviously convex. And it will satisfy the crucial property, namely that for all x, y in V, if x plus y half lies in this intersection, right? So let's now say F is a set of faces of a given convex set. And now I take the intersection over this. So if this is true, then x and y are both again in this intersection, right? Because why is this the case? Because this here implies that for all f in F, for all faces in this system of faces, x plus y half lies in F, right? So, but we know also that this, because F is a face, this implies that x and y lie in F, right? So, therefore, I can also deduce, in particular, that for all f in F, x and y lie in F, which means then this here, right? Okay. Good. So that was easy. And now let C be a non-empty convex compact subset of a locally convex k-vector space V, when C possesses an extreme point. Okay, so for the proof, so the idea is that we take a minimal face of C, right? A minimal non-empty face, because the empty set is also face. So a minimal non-empty face, right? So, and in order to do this, we employ Zorn's lemma. So so we will then, okay, so we will get a minimal, actually, sorry, I forgot to say closed non-empty face, a minimal closed non-empty face, f of C. Maybe first note that C itself is, it's a face of itself, right? So C is a face of itself. It's also a non-empty face of itself because it's non-empty by hypothesis, and it's also closed. Why is it closed? Because a locally convex k-vector space, as every topological vector space, is Hausdorff, and a compact subset of a Hausdorff space is closed. That was 7 to 6. No, sorry, it was not 7 to 6, it was with exercise 7 to 16. So in a Hausdorff space, every compact subset is closed. So C is is a closed non-empty phase of itself, right? So so a partial order. So we could look at the following system of phases of C, right? So all F closed phase of C and non-empty. And C is an element of F. Okay, so we have this partially ordered set and we want to show that it has minimal elements. So in order to apply Zorn's lemma, we can look at a chain, that means a totally ordered subset of this. Now, and we have to show that every such chain has a lower bound in F. Now, the empty chain has as lower bound every element of curly F, and there is an element of F, like namely C, right? So so the empty chain is okay, but so we have to deal with non-empty chains of closed non-empty phases of C. Okay, and so with non-empty chains in this partially ordered set. And in this case, the lower bound we will choose is the intersection, right? If I intersect over such a chain, then it is again is again a phase, right? By this remark, and the only question is if it's again a closed non-empty phase. So closed is also okay because an intersection over closed sets is closed. And so we have to show that it is non-empty, right? Yeah, remember, we are still showing this the existence of this minimal closed non-empty phase F of C, and with that we will then proceed. Okay, so if the intersection over such a chain were empty, then a finite sub-intersection would be empty by the compactness of C. 5, 1, 14, right? So because here, so 5, 1, 14. Remember definition of quasi-compactness, right? Hausdorff is here anyway. I mean, V is Hausdorff if V is a topological vector space. So I'm just speaking about compactness because it's equivalent to quasi-compactness. A subset of V is compact if and only if it's quasi-compact, because the Hausdorffness is for free here. And I don't want to say the quasi every time, but really what we need is the quasi-compactness of C. And that means that every open cover possesses a finite subcover, right? So, but if you are looking at what that means, if you formulate it with closed sets instead of open sets, I mean closed sets are the complements of open sets. Then this means if you have an intersection of closed sets that is contained in the complement of my quasi-compact set, then there is a finite intersection that is already contained in the complement, right? Okay. Yes, so in particular, if I have an intersection which is empty, if I have an intersection of closed sets that is empty, then a finite subintersection would be contained in C. But I have been intersecting here subsets of C. So if a finite intersections of subsets of C is contained in the complement of C, then it has to be empty, right? So I guess I use here also that C is non-empty. So indeed, if an intersection were empty, then a finite subintersection would be empty by the compactness of C. Little exercise, right? Which is impossible since we dealt with a chain, right? Okay. And a finite subintersection would actually be an element of this chain, right? And therefore cannot be empty. Okay, so now we have this minimal closed non-empty face, and we hope that it's a singleton set, right? And so being a closed subset of a compact set, F is compact itself by 5, 1, 21. Yeah. Right, closed subset of a compact space is compact itself. Okay. F is compact itself by 7, 3, 7. It suffices to show that there is exactly one element because singleton face is an extreme point, 7, 3, 7. Yes, 7, 3, 7. Here it is. X is an extreme point of A if and only if a singleton set with X, if the only element X is a face of A. Okay. Yeah, so because F is non-empty, it suffices to exclude that F has at least two elements, okay? So assume the contrary is true. It has at least two distinct elements, X and Y, let's say. Then I want to show that this contradicts the minimality, right? So, I actually will then construct a face, a subface in some sense, but the face of this face, that will then be a face of the original set, that means C. So I will construct a proper subface, which contains X but does not contain Y, I guess, or the other way around. Let's see. And the idea is a little bit like one way of constructing faces sometimes is by taking such a linear function, such a k-linear function, and looking at all the points of a convex set where this function gets minimal, right? So in this way you can construct exposed faces, and we know that exposed faces are faces that we have proved already. So that's a bit the idea here, and I actually take it actually will not be exactly like this, we will see why, but certainly it would be a good idea to look at the continuous k-linear function, because then I might, I can then maybe apply this f is a non-empty compact set, and continuous functions on non-empty compact sets attain a minimum somewhere, right? But first let's construct this continuous k-linear function. So for that I use maybe a tool that seems a bit too exaggerated for this purpose, but anyway, since we have it, let's use it. By 735, that was a separation theorem, I can actually separate the singleton sets x and y in this locally convex vector space. So 735. Yes, so at least we use here the local convexity, so it's good. We should probably use it somewhere, right? So if you have non-empty convex sets in a locally convex k-vector space, which are disjoint, and one of them is closed and the other one is compact, when we have this strong separation here, when there is a continuous k-linear function strongly separating this here. Okay, so in our case, with separation, since we deal with singleton sets, the singleton set with x and the singleton set with y, right? They are both, with every singleton subset of V is actually closed, right? That we know already from the definition of topological vector space. And such a one-element set is also compact, of course. So we can apply this and we get a continuous k-linear function phi from V to R such that phi of x is less than phi of y, right? I mean, if in the theorem I had even with R and with S, but yeah, in the very particular case that we have here with R and with S do not give any further information because A and C are singleton sets in our setup here. Okay. So when I take G to be, the idea was to look at this set where phi is minimized on F, and this is non-empty because F is compact and non-empty, so by 7119. Okay. Yes, right. If you have a continuous function on a non-empty quasi-compact topological space, it assumes a minimum and a maximum. In our case, we need a minimum on this set. So yes, so G is therefore, by definition of an exposed face, is an exposed face and then also a face, right? By 7310, every exposed face is a face. Okay, so we don't need the exposedness anymore, we just need a face. Hence, G is being a face of a face. It's also a face, right? G is a face by 7.3.12. Right? Okay. And from a continuity of phi, we deduce that G is F, right? F intersected with intersection over all W in F, right? So maybe I should. So with F here comes from this condition, right? And this intersection here corresponds to it universal quantifier here. Intersection over all elements in the preimage of the interval minus infinity, from minus infinity to phi of v. Well, that's just another way of stating this equation here, right? Why did I state it in this way? Because I want to deduce that G is closed. Yeah, and that I can deduce from the continuity of phi, because since phi is continuous, this is a preimage of a closed subset of reals. So it is closed in V. And here I have an intersection over closed sets, that's again closed, and F also was closed, and therefore, right, F was also closed, and therefore G is an intersection of closed sets and is therefore closed. Okay, so G is closed. And it's an exposed face of F, and it's non-empty, right? It's non-empty, so it's yeah, it's yeah, and it's a subset of F. Because F was minimal closed non-empty face F of C. We have that G equals F, but that's not possible because X and Y were both elements of F, but here I claim that Y is not in G. Why is Y not in G? Since phi of Y. So if Y were in G, right? If Y were in G, then we would have that for example, phi of X is greater than or equal phi of Y, right? Phi of Y, yes. But that's not the case. Yes, therefore G is a closed non-empty face of C that is properly contained in F. That's a contradiction to the minimality of F. Okay, so yeah, that proves our lemma, which says that every non-empty compact convex subset of a locally convex k-vector space possesses an extreme point. Okay. Yeah, so now we go to, we need some notation for a set of extreme points, and we are still heading towards the Krein-Milman theorem. So let A be a convex set in a k-vector space V when we write X of A for the set of extreme points of A. So suppose, so now another theorem before we come to Krein-Milman, that's actually a theorem that, yeah, I guess it's a sharpening of 7.1.19. So let's first have a reminder on 7.1.19. So that should be here somewhere. Yes. So 7.1.19 was if we have a non-empty quasi-compact topological space and f a continuous function on it, when f takes on a minimum and a maximum, right? and in a certain on a minimum and a maximum on M, right? And here we have a more special situation. Here we are our quasi-compact, non-empty quasi-compact topological space is actually a non-empty compact convex subset of a locally convex k-vector space V. And our continuous map is a continuous k-linear function into a k-vector space of reals. And in this case, phi attains on C a minimum and a maximum in an extreme point of C, right? So that's the new thing which we can do better in this special situation. Namely, we can do this in an extreme point of C, right? In other words, there are x and y extreme points of C, such that phi of x less than or equal phi of z less than or equal phi of y for all z in C. So for an example, let's look at the square again, right? And then so let's take the unit square and sorry. Okay, and now phi, how can we think? So that's again in the R vector space R2, right? And if I have a linear form on it, that means an R linear map from R2 to R. I take for the field K, I take the reals. When this looks like when the kernel of phi, if phi is not the zero map, then the kernel of phi looks like it's a line through, it's a straight line through the origin, and then here maybe that's the set where the kernel where phi takes some positive fixed epsilon, right? And then here's it where it takes 2 epsilon and so on, right? And you see here there is a unique point where phi gets maximal on the square. That's this point here, right? And this point is in fact, it's exposed. So the situation could have been different if this square or the linear form, okay, it doesn't matter what. So if a linear form is like this, right, for example, when the set of points where it is maximized is actually here, set of points of a square where it is maximized is all this, right? And then not every maximizer, right, is an extreme point, but there are maximizers that are extreme points, namely this and this. And the theorem says that if you are in a locally convex k-vector space V and phi is continuous, then that's always the case. When there is always a maximizer, that is an extreme point, right? So let's look at the proof. So okay, so one could yeah, replacing, if you want, phi by minus phi, we show only, suffices to show the existence of an extreme point that minimizes, I chose here to minimizes phi among all points of C. Yes, for yeah, so there is such a point that minimizes by 7119, but I don't know if it's extreme, right? So there is a y in C that minimizes phi among all points of C. So in an example, if this is if a blue set is my convex set, right? When phi, so this should be the kernel of phi, and this should be the level sets of phi, right? And here phi gets smaller, and here phi gets bigger. And so what I define as so I just know the existence of this minimizer y, and it could be this one, right? And now, but I don't want to fix this actually. I don't want to fix this. Instead, I look at all such minimizers, right? So that's so in our picture, I look instead at all these minimizers, and I call the set of all such minimizers F. Okay. So that's why I use here again the letter y, because here this I don't want to fix this y now. Okay, so so how do I get now an extreme minimizer? Yeah, so an extreme minimizer. So how do I get this? Yeah, the idea is just to take an extreme point of f, but why does f have an extreme point? Well, f first of all is non-empty, you know. So now, you know, because we had this point here already, here, this one. So since phi is continuous, so of course we want to use now, you know, the lemma that compact convex subset, non-empty compact convex subset possesses an extreme point. So actually phi f is by definition an exposed face of C, and therefore it's a face, and therefore it's convex, so it's non-empty and convex. But we need a closedness, and we need we need the compactness actually, right? So compactness. Now, why is it compact? Well, now it's of course important that C, our set C was that we required C to be compact, right? C was compact, so why is now F compact? Well, that's because it's a closed subset, it's closed in C, and it's and therefore it's compact, right? So you know, and when we have to argue, okay, so we will use that closed subsets of compact topological spaces are compact. So for this, so we need actually closedness of F in C, right? In the where C is equipped with the topology induced from V, right? With a subspace topology. Okay, so we write F as, you know, that's the old trick. We write it as C intersected with this intersection here. So this intersection here, our set in C corresponds to this universal quantifier of pre-images of this interval minus infinity phi of z. That's a closed interval in the reals. Since phi is continuous with pre-images closed in V, right? Now you could intersect it if you want with C here, when it is of course closed in C, right? And now you have an intersection of closed subsets of C that's again closed in C. So and so F is closed in C as a closed subset of a compact set C. It's itself compact, right? Now by lemma 7314, it's of course also convex. It possesses an extreme point. Oh, so now we get an extreme point of C, right? For example, this one, or maybe that one, right? And this is, this is also an extreme point of C, right? Because if you call that point here, if you call it X, then that X is an extreme point of F, just means that the singleton set X is a face of F, but F was a face of C, and we learned that being a face is transitive, right? So from these two we conclude that a singleton set with X is a face of C. And therefore it's an extreme, X is an extreme point of C. Yeah, and so now that's an important lemma, and now we come already to a Krein-Milman theorem. Suppose that C is a compact convex subset of a locally convex k-vector space V. Right? When C is the closure of a convex hull of a set of its extreme points. That means, C is the closure of a convex hull of a set of its extreme points. So I don't want to go into details why we need a closure here. I mean, in the proof, we will just prove it for the closure. And why we need it, I don't give intuition about that. But later on we will prove for a special case of a finite dimensional k-vector space V. We will later prove that the same thing is true even without the closure. Here, right? That will be Minkowski's theorem, which we will treat next time, and which sometimes people also call Krein-Milman theorem, although it's really due to some more early work, and the proof is actually quite different. Yes. And I mean, without the so the problem is that when we think about it using pictures, we always think of a finite dimensional case, and so you can illustrate this theorem quite easily in the finite dimensional case, right? So let's look at this convex set, for example. Okay, such a the intersection of a unit circle with a quadrant, if you want, right? So what are the extreme points? So this is an extreme point, this is an extreme point, and every point here is extreme, right? So what I draw in black is the set of extreme points. C, if C is this compact convex subset of the R vector space R2, then a set of its extreme points is this, and if you take now a convex hull of this, then you get back C, right? Even without a closure. Okay. So, and that with a closure, that works even in locally convex k-vector spaces. So let's look at the proof. So one direction is, of course, trivial, almost trivial. because the extreme points of C are certainly contained in C, and the convexity, because of the convexity of C, we get that the convex hull of the extreme points of C, of a set of extreme points of C, is still contained in C. Now C is closed because it's a compact subset of a Hausdorff space, right? Topological spaces are always Hausdorff. And that entails that you can even take the closure. So the closure of a convex hull of the extreme points of C is contained in C. So that proves the inclusion from the right to the left. And now the other inclusion from the left to the right. So here, if C is the empty set, nothing is to prove. So I can assume C is non-empty. And now let me call let me call the set in question A, right? So I have to show that C is contained in A. So the set A is closed because it's closure of something. It's non-empty by the lemma because there is an extreme, C possesses an extremal point by the lemma, right? Yeah, since C was compact. Okay, so it's closed, it's non-empty by the lemma, and it's convex, since the convex hull is of course convex, and the closure of a convex set remains convex by 7 to 13 because we are in a topological, that's true in an arbitrary topological vector space, right? Okay, so yeah, so A is closed, non-empty, and convex, right? And we have to show that C is contained in A. And equivalently, I can show that the complement of A is contained in the complement of C. So let X be an element of a complement of A. Separate X from A, right? I will separate X from A with the separation theorem for locally convex vector spaces. So let's look at that separation theorem again. So okay, so in this separation theorem, we take a continuous k-linear function. We get by this separation theorem, we get a continuous k-linear function phi from V to R, such that phi of y is smaller than phi of y is smaller than strictly smaller than phi of x, right? So here I for C I take the singleton set consisting just of x, and here for A I take A, right? And then yeah, from this I mean I ignore here the R and Vs, so but I get here this, right? So that's all I need here. So by 7, 3, 6, yeah, and I can do this. Sorry, I can do this because C is compact, right? Right. C had to be compact here. C was also non-empty, convex, of course. Yeah, A, I mean, since yeah, since and A, by the way, is also non-empty. Well, if A were empty, then I could take for phi just the zero function, right? But I could also so I don't even need 735. But I of course I can, if I want, I can really apply 735 because A is simply not empty. But I don't need to argue for that now. Why is A non-empty? Because C has an extreme point, right? Why does C have an extreme point? Well, that's again by the lemma 7.3 14, but I don't need it, right? Okay, good. So by 7.3.16, there is even an extreme point of C where phi gets minimal, right? Satisfying phi of z less than or equal, there's a y, an extreme point of C such that phi of z less than or equal phi of y for all z in C. Sorry, actually an extreme point that maximizes phi here, right? Yes, now it follows that phi of z is less than or equal phi of y, and this is less than phi of x for all z in C, right? Yes, so in particular x is not in C. Okay, good. So we will use, well, we could actually use the Krein-Milman theorem, but we will actually use just theorem 7.3.16 in a very important special case, namely where V is the vector. So don't get confused. The blue V, right? The Krein-Milman V here will be R will be an R to a red V, which is a different V, right? And and R to a V carries, that's the vector space of all functions from V to R, and it carries, of course, product topology. And yes, so that's and for C we will take the state space. We will take the state space of red V and of red V and another C, a red C, right? Namely a cone in the K vector space V. Yes, and then I will have an element U of V, which later will be a unit but can now be arbitrary, right? So this is quite that leads maybe a lot to confusions, right? Because R to a V, okay, so that's why I talk so much about it. R to a V is an R vector space, whereas V can be a K vector space. Yeah, and these are two different cones, right? So here I have red C, and here I have another cone, right? So we will apply 7, 3, 16 in the case k equal r actually. Yeah, I guess when I said again, I will apply Krein-Milman, but I will actually apply 7, 3, 16. Sometimes in the literature, people apply it with occasion. Krein-Milman. Okay. And yeah, we have to check why this is actually a compact convex subset of this R to the V. More or less we did that already. I mean, yeah, if U is a unit, it will be like that, right? So we will actually also assume then that U is a unit if we apply Krein-Milman, a unit for C. Okay, so and in particular C is a cone. So definition 7.3.18, let V be a k-vector space and C a subset of V. Here it can still be an arbitrary subset, but soon it will be a cone again, and U is an element of V, but soon it will be a unit for the cone C. We call an extreme point of a state space. Yeah, you remember what that was? That was the k-linear functions from V to the reals that map C into a non-negative reals and map U to 1, right? There was no topology here involved. And we call the extreme points of his state space pure states, right? So I mean, that's a convex set, so it makes sense to talk about its extreme points, and we call them pure states, right? And so the idea is that, comes exactly from this Krein-Milman theorem, because why you call them pure states? Because, by the Krein-Milman theorem, every state, right? Every state can be approximated with respect to this topology by convex elements in the convex hull, by convex combinations, can be approximated arbitrarily well by convex combinations of by convex combinations of pure states, right? So that's so the idea is more or less that with pure states would be something like building blocks, and all other states are somehow, at least approximately, are built from these pure states, or somehow mixed states, right? So our terminology, I guess, that comes from physics, from quantum physics probably, but that doesn't, that's not important for us now. Okay, so now using this, again, we can now formulate the last theorem of this section. And that's actually a strengthening of a theorem we had already some while ago, namely theorem 7.1.20. So maybe let's first look what was 7.1.20. Okay, so 7.1.20 was actually here. Okay. I mean, that was already a strengthening of something, but okay. Okay, so 7.1.15 was 7.1.20, sorry, was the following. Let U be a unit for the cone C in the k-vector space V and X in V, when the following are equivalent. First, for all states of VCU, phi of X, all states map map X to something positive, right? And And second, there exists a positive integer n such that x is in 1 over n times u plus c. X is of a form 1 over n times u plus something in c. And third, x is a unit for c, right? This was this equivalence. And we will now make this, the non-trivial implication, I mean, the hard implication was, from A to B, for example, right? And we will now strengthen this non-trivial implication by saying that you have to do this test here only on pure states instead of arbitrary states, right? Okay, so I take here just pure states here for this test. Yeah? And here I could also take all states, right? That was the previous condition here. And when C here corresponds to B here, it's exactly the same condition, in fact. And then, of course, here I have one more condition, namely X is a unit for C. So what got better here? That, I test only on pure states. And that will be, I think I talked already once about it, because in our application, we will want to have that we want to test only on phi's that are, for example, multiplicative or satisfy some kind of multiplicativity. We will come back to this later. And that will actually have to do with this property that we look only at pure states. That will lead to some kind of multiplicativity. We will see this later in special situations, of course, right? Okay. Because multiplicativity makes here no sense. I mean, phi is real valued, so on real numbers I have a multiplication, but on V I have a priori no multiplication. But later we will apply it to situations where V is at the same time, for example, a commutative ring, or actually an ideal of a commutative ring, and then I have some multiplication on V. Okay, so so now let's prove this, and of course we will use 7.1.20 in the proof, and we will use the theorem 7.3.16, which was the theorem before the Krein-Milman theorem. Okay, so B implies that these three conditions are equivalent. That is already 7.1.20. Okay, so the only thing, so B implies A is trivial, of course, right? And so the only thing to prove is A implies B. Okay. So without loss of generality, there is a state, because so if there is no state, then there is no if there is no state, then this is the empty. This is an empty statement, and I have nothing to prove. So without loss of generality, there is a state. And it suffices to show that this function from the state space to the reals that maps phi to phi of x attains a minimum in an extreme point of a state space, right? Yeah, because if that is true, then in this minimizer, in this extremal minimizer, in this pure state minimizer, phi has a positive value. But that's this value is the minimum, of this function, and therefore for every state phi of x is positive. Okay. Okay, so but this follows from 7.3.16 because S of VCU is a non-empty, right? Non-empty, compact, convex subset of the locally convex R vector space R2V, right? So we have already seen all these things in 7.1.17 that it is compact, 7.1.16 that it is convex, that's almost trivial, and this was a locally convex R vector space by 7.2.2a. And yeah, now we have this yeah, so and yeah, and yeah, I use also one thing that this function here is continuous, right? But that's by the definition of a product topology simply. Okay. Yeah, and that's it. And now we have finally we have yeah, we can make a version of this which is which seems weaker, but which is more easy to state. So, and that's actually, that will be a strengthening of 7.1.15. 7.1.15 was membership criterion for being contained in a cone which possesses a unit, right? So that was this theorem here. So suppose U is a unit for the cone C in the k-vector space V and X is in V. If phi of X is positive for all states phi when X lies in C, right? And now we can formulate the same thing, exactly the same thing again, except that instead of states, we need just to test on pure states, right? Okay. So you see it's exactly the same theorem, right? It's exactly the same theorem, except that you have here pure states, right? So that's the advantage. Okay. So, and of course that follows from 7.3.19, you know, if B is satisfied when X is actually in 1/n times U plus C, and since U is a unit of C, a positive scalar multiple of U is of course also in C. I mean, U is in C when this positive scalar multiple of U is in C, and when C is in C is closed under addition, I see that X is in C, of course, right? Okay, that's it for today. Thank you for listening, and next time we go then to finite dimensional k-vector spaces where k is a subfield of reals. Yeah, thank you and goodbye.